Good morning. So I'm Alexandra Oliveira. I'm just a little bit of my background, so to have a better context about this talk. I am a data scientist, but also I am a professor at Polytechnic of Porto. Sorry, my bag is hitting me on the leg. I'm a professor at Polytechnic of Porto. I work a lot of my years in health sector. It is a particular kind of data. And today I'm talking, showing you a little bit of the data science project that I did in the collaboration with colleagues, some colleagues of mine and a student. My student is finishing his master, her master. And this is a little bit of this work in time series that is a special kind of data. So today I'm going to show you a little bit of the time series clusters, the problem itself. What kind of data is this? What it brings special to this context? The problem itself, what we were trying to achieve, what trying to learn, and the approach that we did, and some results and main conclusions. So let's start with the problem. What we're trying to achieve, trying to model. We're trying to model the years lost due to a severe illness or early death. That was our key factor, our outline, our data, that main concern that we're trying to model. Just a bit of context. What you are seeing here is the burden of disease due to several kinds of diseases. In blue, you have the disease non-communicated, such stroke, diabetes. Most of these diseases are linked to habits, and then they could be changed and bring better health to the communities. In red, you have community diseases, the infectious diseases that transmitted person to person, and they are out of the scope of this project because they are really difficult to model. And in green, you have accidents, falls, self-harms. Therefore, what you can see from this chart is that the burden of the disease due to communicated, non-communicated disease is large in all countries of European countries. So this is the cumulative for all the countries in Europe. So we were trying to see these communities, and we start to think if what is happened here, all the countries are the same, what will be the future? And that was our questions that we tried to model. Will this burden of disease still be the same in the future? All the countries are the same. Can we cluster or group countries that have similar patterns? So that we are able to predict the future, we need to know the past. So, and need to focus on the most important things and informations. So, in this image, what you see? If you focus on the light patterns, you will see a skull. But if you focus on the dark ones, you will see devil kittens. So the information that we focus will bring us new information, will bring newer ideas, will show different patterns. If you have this kind of information, what is similar? What will be the most similar objects that we can group? Which groups will be needing to do? So we use this law of similarity, and we're trying to see, of course, if you focus on the shape, we'll need the clusters of the squares. If you focus on the triangles, we'll have another groups. If you focus on the color, we'll have another group. So different groups will be different solutions according to the criteria that we need to focus more. And if we have time series, A time series, I don't know if you are familiar with the terms, but a time series, a graph is a line that shows the patterns through the different years. Here in these charts, you have each line is a time series of the burden of the disease, a particular one, these cardiovascular diseases that we choose to model and to show to you, represented in the country. So what we see in this chart that is there tends to be a cluster here. It seems for me that these lines are grouped together, but we have different patterns and different lines that we don't know how to cluster and to group. And we don't focus on the whole time series and focus just in some characteristics of the time series. Maybe the trend. Here we have some different trends. Each of these graphs is a trend for a particular country about this disease that we're trying to model. It is better to cluster these trends despite or these ones. What would be better? What groups can build upon these trends? But if we can compare two trends of similar patterns, how can we group new groups? Given a new time series, which groups should we cluster in, include this pattern one? The final key is, what is a good solution? What is a good solution for a cluster? I don't know if you are very familiar with the clusters, but cluster is an exploratory approach. So sometimes the clusters are natural and we can create groups of similar and homogeneous things, objects. Sometimes they are not, and they are somehow heterogeneous. So the time series clusters focus mainly in 4 keys. That is a representation of that pattern, that line, the way we consider two lines similar, the way we group and form the time series, the groups of time series, and finally, the way we evaluate the solution created. Cluster is a group is included on non-supervising algorithms. So we just need input data without label, of course. And there are many approaches available: hierarchical, k-means, and principal components. The main use cases of this approach are recommended systems, the anomaly detection, cluster segmentation, also to prepare data to other analysis. So this approach is based on 4 key aspects: the representation methods, the way we are providing the information to the algorithms. And here we have a lot of approaches. We have standardization, dimension reduction, univariated models, also smoothing, fixture extraction, and also business rules. We can focus in several key aspects of that time series. In terms of similarity measures, we have several approaches also that can be clustered in 2 major keys. The first one is in time or shape, when we have the most famous Euclidean distance, so dynamic time wrapped, and also some distance or similarity measures based on models, such as Piccolo, Maharaj, LPC. In terms of clustering approaches, the way we form groups of things that we consider to be similar. We have hierarchical, partitional, and hybrid approaches. In terms of evaluation, we have silhouette, Macaulay-Kelsey, index, Dunn, and business rules. So the combination of these four key factors will produce different groups or approaches. For this talk, this is a large world of time series clustering, and I focus here in some specific parts of these 4 key indices. In terms of representation, we will approach using univariated models, the distance based on those models, the hierarchical, and then all the measures, because of course they have different approaches and different strategies. Why we are doing this? This approach is model-based and univariation models representation allows us to see the future and to try to group time series with that in mind. What will happen, not what we observed here in the present or in the past, but what we could do in the future. So to do this, what was our approach? We collected data from a public repository, and then we prepare, analyze, do the exploratory data analysis to try to identify missing values or outliers that might introduce some noise in our approach. Then we fitted ARIMA models. I will not discuss in detail this fitting approach. If you like to know more, then in the coffee break, I'll be happy to discuss with you this ARIMA approach. And then use the parameters of each model to cluster or find similarities between the time series. Use several techniques of clustering, all within the group of the hierarchical clusters, and then evaluated with all the indexes that were available to try to find a consensus of these groups. How did we do this? We used a lot of Python packages from the stat models and pmdarima to find the best models to represent each time series. We use tsclust and then scikit-learn to fit the best models. Use tsclust, pmdarima, and bclust. And bclust was to find the best, to evaluate the solution of clustering, and then pandas, numpy, seaborn, and matplotlib to represent the information. So, for the disease that we are trying to model, that was cardio, we are expressing here in this presentation, we obtained a lot of models. We obtained each model for each country. Of course, these ARIMA models are very different from each other's. They are simpler models represented here in Denmark. We use a little bit a light model, but in other countries we needed a more heavy model to try to describe the patterns that we were observing, such as the ones in Austria and Azerbaijan. We evaluated each model with 5 evaluation metrics: AIC and ABIC, that is amount of information that model can capture, and then the traditional maze, RMSEA, and MAP. Here it shows to fit or focus on the map, because we have a lot of countries, a lot of time series with different values, with different approaches, different trends, and map allows us to better compare each model without the influence of the values itself. What we find in this way is these simple models, univariated models, are better fitted to countries like North Macedonia and Azerbaijan, and ill-fitted, not poorly fitted, not ill, because they are good models, but less good models to describe the patterns observed in Denmark and United Kingdom. With these models, we choose 3 different similarity measures. The Piccolo, it is a measure similar to Euclidean distance. It's inspired in the Euclidean distance, but applied to ARIMA models. We used also a Maharaj and LPC, and we explored all solutions between 2, because one solution, one cluster is pretty inefficient, and 15. We explored these numbers and tried to be between 2 and 15, what would be the best number of clusters. This evaluation have This approach has two objectives. The first one is to find the best number of clusters that the data allows, and also evaluate the final solution. Because when we look to the patterns that I showed you before, we look and we don't know how many groups we could extract or would be needed to extract from that kind of data. So with these three distances, we use all the clustering techniques that were available: the word, the complete, the single, the average, the centroid, and median, and all the available indices to evaluate the solution. What you are seeing here is the best solution for this index and this method. So the word method for the Maclaurin, according to the Maclaurin perspective, would be 2. Then for the C index would be 15, with the silhouette would be 15, and also with done would be 2. What we do with this lot of numbers for every approach, we focus on each approach and selected the majority of votes. If, for example, for the word and Piccolo distance, we would find 15 clusters, the best solution that would be available for this approach. And then the complete, the single, the average, and therefore. What we're trying to see is what is the influence of the distance on this creation of these clusters, and also what was the influence of this method. Of course, different distances have different solutions available. And then, what would be the groups that was formed later on? So here you are seeing the Piccolo distance. Just focus on the Piccolo distance and the several approaches that grouping approaches that were fitted. So here we have the Piccolo distance with the word method, the complete linkage, the single, and therefore. What we are seeing here, traditionally Piccolo gives a lot more clusters than the other distances and a lot of heterogeneity. There are some patterns that can be extracted. In this award method and the complete linkage, it tends to be a group cluster here in the east. And the single method and the average method typically cluster all the groups, the countries together, and leave Latvia alone from some reason. Let's see the patterns with another distance. Here we have the Maharaj distance. And what we can see at this method, the word and the complete, always trying to extract a lot of clusters, but the others groups, algorithms, techniques, typically cluster a large group with all the countries, and again, Latvia alone. And this is also true in the last distance. The last distance, also the typical these algorithms leave Latvia alone, and then there are 15 groups a little bit different. What were the main findings? We saw cardiovascular diseases, of course, but we saw and analyzed a lot of others. And what we learn about these clusters, about the non-communicative diseases in Europe. In terms of the diseases itself, we learned that countries with similar diseases progression patterns tend to cluster together, revealing shared health factors like healthcare systems that are similar, environment condition, and social economic influences. Austria, France, Greece, Ireland, and Spain frequently across all non-communicative diseases were grouped together. Latvia, Poland, and Greeceland often form distinct clusters away from the other countries, indicating a unique pattern, health patterns, or even a unique health system or reporting notification system. Countries in the same region, Western or Eastern Europe, frequently cluster together due to shared policies and lifestyle policies. In terms of impact of distance and clustering algorithms, distance measures sensitivity. Clusters outcomes are significantly influenced by the choice of distance measures, which capturing different aspects of the data. Some focus more on trends, others tends to focus more on seasonality, some are sensitive to noise, and others are insensitive to noise. The clustering methods, of course, form different clusters. It's also are sensitive to the distance, but also to the time series itself. Countries with similar, in terms of ARIMA models and public health implications, countries with similar ARIMA models behaviors may benefit from shared health strategies and collaborative research. Countries in unique clusters may require tailored interventions due to distinct disease dynamics. So, that's all. And I don't know if you have some questions to me.
Hello.
Hello.
Thank you for the presentation. In the beginning of your presentation, you mentioned that modeling infectious diseases was really hard. Why is that? And also, how are you getting the data for this project?
This project, the non-communicated, is a public repository.
Yes.
Is ARIMA. Then I'll give you a link if you like.
Okay.
Diseases, communicated diseases are harder to model because of the interaction of the individuals. It's hard to model and to capture the number of interactions that are available between people, and it cares a lot more of data. We need more data to try to analyze and predict what will be the next number of infectious diseases.
Okay, thank you.
You're welcome.
First of all, thank you for the presentation. It was really interesting. I have 3 questions, but
okay.
The first
we have
one.
Time.
The first one, what's the period for the data?
Yes. Yes. It goes real fast. The data was available since. Let me just show it to you, since 1990 until the present.
Okay, but the question is, it's grouped by year, by month. Because the first
year.
Okay.
Yes, okay.
The first question is: are you concerned about some seasonality? For example, if we talk about heart disease in December, in Catholic countries, we have more heart attacks.
Yeah.
For Christmas, for example.
Oh.
When comparing to other countries and other cultures, and are you concerned about this trend or this kind of seasonality?
We are not able to see the seasonality in terms of month because we use here data, but the models itself can capture the ARIMA, and the ARIMA models can capture seasonality and trends real nice. Yes, that kind of patterns would be imprinted on the models itself.
Okay, the last question. Did you check about other social information, for example, culture, for example, social index from the countries to see any kind of trends that are not considered only on these numbers, on these rows?
No, we were just using the time series itself. We were trying to model in a lightweight as possible, try to see with the lack of data what we would be able to achieve in the end. So, of course, this is the preliminary study which could benefit all other contextual data about the diseases itself.
Thank you very much.
You're welcome.
No more questions? No? Thank you.
You're welcome.